So yesterday we had finished by stating this theorem that, let's recall what it tells you. We have noticed that if we work purely at the level of sets, the product of two conjugacy classes, say C and D, where C is the class of X and D is the class of Y, is a union of conjugacy classes. This is easy enough. But then we saw in an example that we'll then rework with this formula, that if you take the two non-trivial conjugacy classes in S3, for instance, say the class of 2 cycles and the class of 3 cycles, then their product is the class of 2 cycles, but this class appears twice. Okay, and how do you keep track of how many times the class appears? If you do it at the level of sets, you have no choice, because I mean, in a set, an element either is there or is not there. There is no multiplicity. Whereas if we work as we are doing here in the group algebra, in the center of the group algebra, then we can really see that we can detect the multiplicities. Okay, because this is the sum of the elements of the distinct element of the conjugacy class of X. This is the sum of the distinct elements in the conjugacy class of Y, and this factor will tell you how many times the sums of the elements of a conjugate class of Z, in this case, appears in this product. Okay, and we know that this product has to be a linear combination of these, because we are working in the center of the group algebra, and this element, these sums, are a basis for this. So let's try and get this formula. To get this formula, one has to recall the something that we have used several times. So proof. Let's switch to black. Yes. Otherwise, you think that there is something peculiar about this. So recall that we have exploited several times, and I will probably do it at least once again, that there is an algebra isomorphism between the group algebra and a direct sum of matrix algebras. So M, I have to specify the size, and at this stage we can take the sum to be over the reducible character of G, and then this will be the dimension of this matrix algebra. So this is the algebra of the square chi1 times chi1 matrices. Okay, and we take the convention that that chi of G, say, is the trace of rho of G. So rho stays for a representation that affords the reducible character chi. Okay, so we have this algebra isomorphism, which is actually very simple, because I mean, it's enough to see what it does on G, and this sends it in. So this will be an n-tuple of sorts, indexed by the reducible character, and in the chi components of this thing, you will find simply rho of G. Okay, so in an invertible matrix. So this means that G goes into a tuple, which at the position chi in this sum has rho of G, rho being a representation that affords chi. Okay. And then remember that what I was saying a moment ago, that if we restrict to the center of the group algebra, okay, since this is an algebra isomorphic, this goes to the center of this object. What's the center of this object? Well, it's the direct sum of the centers of all these matrix algebras. And we know that the centers of these matrix algebras is given by the scalar matrices, diagonal matrices. So this means that we have we can say direct sum of irreducible of G copies of C, where we see essentially I write lambda an element of C for what is really a square matrix of the proper dimension. And let's recall exactly where things go. So let's consider a class, okay? Because as I've said several times, this center is a vector space which has as a basis the sums of the conjugacy classes, okay? So the dimension of this is the number of conjugacy classes. And what happens to the sum of a conjugacy class? So suppose G is an element of G, and the conjugacy class of G consists of these elements. And of course, sorry, there's the usual trick that we have to specify that these are distinct for, say, of size n. Okay, so means these elements are distinct. The named elements are distinct. Otherwise, we could write, we could be writing n times the same element. Okay, and so this sum of the element of G, of the conjugacy class, which explicitly is just the sum, okay, goes under this isomorphism, which is just the restriction of this isomorphism to the center. It goes to the sum rho of Gx1 plus rho of Gxn. Chi meaning the component where I am, okay? And so this will be, let's concentrate on a component, okay? Just a second. Yes. Okay, so this is it. Let's copy this to the next. Okay. And we know that this, let's fix chi rho, okay? So rho is a representation of Fordin chi. We know that these elements lives in the center of one of the matrix algebra, okay? This is in the center of the matrix algebra, corresponding matrix algebra. So this element will be A times I, where I is the identity matrix, the appropriate identity matrix. And so let's review what this element is. Well, we can take the trace of both things, okay? And so what we have taking the trace, this is a calculation we have already done, but let's do it again just to be on the safe side. So on one side, you have the trace of AI, which is simply A chi1, okay? Because this is a matrix AAA of dimension chi1. This is the size of the matrix. So you're summing chi times this. And on the other side, you have the trace of this. Yes, okay. So taking the traces, I have the sum of the characters. The traces be linear. Okay, but of course the trace is a class function. Let's put a note here. Sorry, the character, the trace, the characters are class functions. Okay, meaning that the value is constant. So how many times do we have this value? It's the value chi of g multiplied by n, but n, recall, I'll be back in a second to this, is just the size of the conjugacy class, okay? Because we decided that we wrote down the distinct elements. So what does this mean? That you have to multiply by this, which is n really, the size of the conjugacy class. Okay, so we have a value for A, which is, let's write it as size of the class times chi of g over chi of 1, okay? So in other words, this conjugacy class goes into a tuple here, where, I mean, in this isomorphism, where C stands for this, for the complex number, which is on the diagonal here, this goes to this element. Let's rewrite this. So say the sum of the class of G goes under the isomorphism onto the element which has on the chi's component this times this over this. Okay, great. So when we have, and I think like different, let me see. Okay, so I have a different notation in the statement and in the proof, but I'll follow the proof because otherwise I'm sure to mix things up. So what is called X and Y in the statement is called then G and H in the proof, but I'll stick to the notation of the proof, otherwise I'm surely mix it up. So when you consider the product of the two classes, because this is what you are interested in, this goes, I mean, this is an isomorphism, okay? So the product here corresponds to the product here. And the product here is simple because we have a direct sum. This is a direct sum of copies of C. So the operations are on components, component-wise. So this goes into the product. And this is the kite component, okay? So our goal is to find and here the notation is slightly different, the components, the coefficient lambda GHW, okay, such that we want to rewrite this. So we want to find on this side the okay, so on this side, we want to find the coefficients Yeah, the notation is changing, but anyway, hopefully is not too complicated. Okay, so we want to find the coefficients that tells you how many times the conjugacy class of an element W appears in this product. But of course, this being an isomorphism, is the same thing to look at on the right-hand side, this being integer, so they stay the same. And so this object will be the transposing this, the sum over W, and and here we'll have okay? Because this object is the image of this under this isomorphism, okay? So we want to determine these elements here, which are sometimes called the structure constant of the center of the group algebra. Structure constants mean that the sum in the group algebra is trivial, is by components. The product is not. So this structure constant tell you how you multiply two elements to get a linear combination of two basis elements to get a linear combination of the basis element. So we want to compute these elements here, but we go here. I mean, after all, that's what isomorphisms are about. If you prefer, you have an isomorphism. I mean, so this is an element in the center of the group algebra. This is in a sum of direct sum of copies of the complex number. You can compute either here or here, where, I mean, it's just a matter of preference, and this will turn handy because we can use formulas that we know. So, okay, so what's the idea? So we have this identity where this structure constant, these coefficients are unknowns. And how do we get to these unknowns? We will use the other or second orthogonality relations. So what do we do? So these are the unknowns, okay, that we have to determine. So we multiply both sides of this object by chi z inverse chi 1 for a fixed z. Okay. For the moment, we don't care about the left-hand side, and look at the right-hand side. So this is shorthand for right-hand side. So we multiply by this. Just a second. Yes, this is square, but okay. So what we obtain on not only. So we multiply. You'll see that chi 1 will simplify for this chi 1, and this will survive. But what we'll do, we then sum over chi in the reducible characters of G. Okay, so let's look a second to what we are doing. We'll ignore the left-hand side for the moment. We'll deal with it in due time. But we take this and multiply by chi z inverse chi 1, okay? So the chi 1 will have simplified, and we will have a chi z inverse here. And then we sum over the irreducible characters. There is already a sum over W, and we have already another sum over the chi. So what will we obtain? We can rearrange the sum as usual, taking anything. So we have two sums. One is over W and one over the characters. With these ranges in a set of representatives of the conjugative classes. So one element for each conjugative class. Okay, and so as usual, when you have a double summation, you can take out of this anything that does not depend on chi. Okay, so what definitely depends on chi will be chi W, okay, and chi z inverse. This you cannot avoid. So here you will have chi z inverse and chi W. Whereas on the left, what's left here will be this part, W of the order of W and this lambda, the order of the class, which does not depend on chi, and this, which does not depend on chi. So here we will have okay. And now the point is that this is, by the other orthogonality relations, this is usually 0, okay? Except when Z and W are conjugate, okay? And then, so there's only one summand that comes out. So all of this, yes. All of these are 0. So multiplying and summing on chi is useful to isolate exactly one coefficient, one particular coefficient. We have fixed Z, of course, but Z is the, well, it's fixed element that varies. So it's an arbitrary element, R0, except when, and we can say Z equal W, okay? Because, I mean, after all, we can choose Z also in a set, in the same set of representative of the conjugacy classes. And what we will have a lambda GH of Z, okay, times, let's write it in the right order. Size this, and then recall that when Z is W, okay, here we will have the order of the centralizer. Okay, these are I don't have them handy here, but these are the second orthogonality relations, okay, or other orthogonality relations. So if you sum over the reducible character, this, you will get 0 normally, except when Z and W are conjugate, and then you get the size of the centralizer. This is something we have used, for instance, to give the first proof of the fact that the order of centralizer do not increase when we go to a quotient group. Okay, and now I have left this as at the beginning because it was here, but look at these two factors. This is just the order of an orbit under conjugacy and the order of the stabilizer. So orbit stabilizer tells you that this is the order of G. Okay. Great. So that's the right-hand side. What's the left-hand side? Is just well, okay. Let's look back. So it's this, but remember what we have done on the right. Of course, we have to do it on the left. So we have multiplied by chi Z inverse chi1. So 1 chi1 will simplify with 1 chi1 here, and we will be left with just 1 chi1 here, and then you'll have this, and then we have to sum over the characters, as we did on the right-hand side. So now, this is the right-hand side, which is lambda G H Z, the order of G. And now let's look at the left-hand side. This will be the sum over the reducible characters of what? I'm copying what we had on the other side. There's a chi Z inverse here and a chi1. There was a chi1 squared, but we have multiplied by chi Z inverse and a chi1, so one simplifies, okay? And now this is already a suitable formula. Usually it is rewritten in a different way, and the way it is rewritten is this. We have a copy of the order of G here, okay? So what we do, okay? So we take this to the other side, so we divide by the order of G. And yes, let's isolate this, okay? Let's do the calculation. Let's leave the other parts unchanged, but note that the red part, okay, if you divide it by the order of G times the order of G, again, orbit stabilizer tells you that you have the one over the centralizers. Okay, it's the usual orbit stabilizer. Okay, so we divide by the order of G. We have just one order of G, so we have to add another order of G. I mean, because we have only one. here. So we have taken these two terms that don't depend on the character outside as usual. And so one order of G goes with this one, say, another one goes with the second order of the class. So we need one on the numerator to balance things. And then here you have simply the sum of the irreducible characters of chi G, chi H, chi Z inverse. So this might look like it's a bit complicated, of course, but it's a formula for the structure constant of the center of the group algebra. I mean, it tells you how they multiply, okay? How the basis element of the center of the group algebra multiply. So let's copy this formula to the next page, because I want to go, if I'm able to do it without errors, because I want to take this particular example. So what's the well, okay, first I mean I'll fix the notes, but there are really two different notations in the statement of the proof and in the statement and in the proof. So in the statement I have x, y, and z. Okay, and here I have gh. This is not a serious problem. In the proof, in the statement, I have something like lambda c, d, e. These are the conjugacy classes. But of course, it's the same to speak of the conjugacy classes or to speak of one element for each conjugacy class. I mean, the idea is G is an element of C, or that is the C is the class of G, and so on. Okay, so I mean, you write it this way or that way, but the correspondence between the two is the same. So as an example, we redo the calculation when G is S3, but I have to have the calculation here, otherwise I'll actually miss it. And so C will be the class of 1, 2, and D will be the class, so this is G, and this will be the class of 1, 2, 3. So this is H, okay? And since we need the irreducible characters, recall that irreducible characters of S3, so we write here the representatives, and they are, there's the trivial character, then there is the character coming from this cyclic group of order 2, from the quotient, and finally there is a character of degree 2, which is -1 here and 0 here. A 0, recall that a non-linear character must have a 0. This is -1 because in the representation, 1, 2, 3 goes to a diagonal matrix which has on the diagonal omega and omega square, which are where omega is a primitive third root of unity, and omega plus omega square is -1. So let's try to work out this formula. So the first thing to do is to see whether the class of 1 appears, okay? And recall that what we expect, we expect to have that sum C times sum of D is twice. We did the calculations already, okay? So we know that only the class C has to appear with the coefficient 2. So we have to do this sum, okay? This coefficient is equal for all. I mean, G and H are fixed, okay? It doesn't depend on Z. So what's this? The order of the group divided by the centralizer of G, which is order 2, and this is order 3. So this really cancels out, okay? Well, no, just a second. This really will be 1, okay? This element in front. And then I have to sum over the reducible character. So I have to sum over columns, okay? So the first thing I have to take here is Z inverse. Let me see, yes. I have to sum of the character, yes. So what's the sum that we get here? So, okay. Okay, so the point is, so the three characters, let's say chi-1, 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 and chi-2, okay, where the index, well, okay, just to learn the things. There's chi-1, there's chi-1, and there's chi-2. So chi-1 means trivial 1, chi-2 means the character, the reducible character of degree 2, and chi-1 refers to the fact that there is a -1 here. And so we have to take okay, so the point is that the contribution of chi2 will always be 0 because h is 1, 2, 3. So chi of chi2 of 1, 2, 3 will be 0. Sorry, okay. So the contribution of chi2 will always be 0 because the value of chi2 on 1, 2 is 0, okay? So when G is 1, 2, this element will be 0. So this is always 0, okay? Also in the other coefficients, just because there is here a chi of 1, 2, okay? A chi2 of 1, 2. But then let's look at the other characters. So we have chi1 of what? Well, in this case, this is 1 for both characters. So we have 1 times 1, okay? And then times 1, okay? Plus, so what's the product of this character is 1, 1, except that for 1, 2, it will, for 1, 2 will be -1. Okay, plus 0. Okay, so this is 0, as expected. Okay, because I mean, in this case, I have exactly the 3 distinct elements. Okay, so I have to take the product of these 3 values in one summand. Okay, because this z is 1, this is 1, 2, 3, and this is 1, 2. Okay, so 1, 1, 1, this is, and 1, 1 minus 1. Okay, fine. Then let's look at what happens when I have GH. So this time we expect a 2. Okay, because it is the class of G, the class of 1, 2 should appear. I mean, in front I have a 1, so I'm not writing it because this does not depend on Z, okay? This time Z is G. So what we have here, so the first thing will be for chi1, we have realized that chi2 won't appear. No, this is chi-1. Okay, so this time Z is the same as 1, 2. So what we get, this is important. Let's write the sum. So we have chi1 of 1, 2, okay? Then chi1 of 1, 2, 3 times chi1 of 1, 2 again, because yes, because G is the same. It will be the inverse, but of course the inverse of this is the same. Plus, now chi-1, chi-1 of 1, 2, chi-1 of 1, 2, 3, chi-1 of 1, 2. Okay, this is what we get here. And chi1 is, I mean, the value on 1 is 1. So what we get here, well, for the values of chi1, the values are all 1. But here what we have, chi-1 of -2 is -1, but it appears twice. And so this, you see, this is 1 plus 1, which is 2, okay? And let's calculate the last coefficient. And once more, we will have only the contribution of chi1 and chi-1, because chi2, as we said, the value on h will be 0. So what we have here, we will have chi1 of, so G is 1, 2, and H is 1, 2, 3. So we have to compute chi1 of 1, 2, okay? Then chi1 of 1, 2, 3, okay? And then chi1 of 1, 2, 3 inverse, because that's the formula. And this is the same with chi minus 1. But if you look at the values, the values on 1, 2, 3 are always 1, okay? And of course, the character being a class function is the same in the inverse, which is still a 3 cycle, whether here you have a minus 1. And so this will be 1 times 1 times 1 plus minus 1 times 1 times 1. And this is 1 minus 1, 0. Okay, and so admittedly it's more complicated than doing things directly, but we have verified this formula for the case of the product of these two classes in S3. I mean, it works. And of course, in more complicated cases, this formula may be useful for computational purposes. Good. And so that's it for this part for the moment. And now we want to move to an extremely important part which deserves a new page, which is induced characters. Induced characters are so important. They play a role in one of the proofs of the theorems with which I want to end this course. They will give essentially two approaches to induce characters. The first approach is via tensor products. So you are surely familiar with tensor products. Let's begin with vector spaces, okay? Over a field, say F. Okay, so start discussing this. And the idea of this vector space is the following. Let V and W, to simplify things, will say be finite dimensional vector spaces over the field F. So a tensor product of V and W is a pair. Well, one normally refers to just to a single object, but is a pair. So is a pair where the first component is well, first component is an F vector space, which we call V tensor. Let's write an F here. Okay, and then a bilinear map. Let's call iota from the product of these two to this tensor product. So what does bilinear mean? So this is just a set theoretic product. It's not seen as a vector space. And to say that it's bilinear, it means that iota of, say, lambda 1 by V1 plus lambda 2 V2, no comma here. There is a comma, but it comes now. W, it's equal to, so it's linear in the first component. No, well, of course, just a second. So it's linear in the first component, meaning that you have lambda 1. Lambda 1. Iota of V1 W. This was I was forgetting the first time. Okay, and the same in the second component. So A tensor product of V and W is a pair, a vector space and a bilinear map with the property that, say, with a universal property, that, so you have this, this stuff, that given any vector space U and any bilinear map in the same sense, which we can, let's call it 5 from V times W to U, so here our 5, okay? There is a unique linear map. No, I will write it here. Linear map, which we can call psi, which makes the diagram commute, the diagram commute. What's the importance of tensor products is that, well, of course, we studied linear algebra, we studied vector space and so on. We know a lot about linear maps. And then it becomes natural sometimes to consider maps that are not just linear, but bilinear, like, I mean, meaning that they are separately linear in the two components. For instance, inner products. Well, inner products, they are actually sesquilinear, but it's more or less the same. And the tensor product tells you that if you are interested in the bilinear maps or multilinear, because we could have more factors from the pair VW to another vector space, an arbitrary vector space, you have just to care about one bilinear map, this iota, and then all bilinear maps here will really correspond to a linear maps here, okay? So you want to study all the bilinear maps coming out of VW to an arbitrary vector space, to any vector space, then you have only to know one particular bilinear map, and then once you have this, all bilinear maps will be reduced to linear maps, okay? So it's given V and W, there's only one bilinear map you are interested in, which is this, okay? And then the rest, and then bilinear maps become linear, okay? And you have studied, I won't go through the construction of the vector space. For instance, one proves that the dimension of the vector space, recall that everything is finite dimensional. Here is the product of the two. Well, let's say over F, okay? And moreover, this tensor product, I'm just recalling things that you have seen in other courses, is generated as a vector space, as an F vector space, by the elements, by certain elements that we call the V tensor W. This is a small tensor, which is actually iota V W, where V is in V and W is in W. We could actually choose V and W to be bases of the two, but this is not very important. And moreover, this being bilinear, we have this property. Okay, we multiply by scalars on the right. No, sorry. And we'll have this property that VA times W equals V times WA. Okay, let's put parentheses for, well, V in V, W in W, and A in F. Okay, so we can move the coefficient to the right, from the left of the tensor symbol to the right of the tensor symbol. Oh, and moreover, this is a vector space, and okay, I'll write this here. What happens when you multiply by, no, I'll write it in a different place. Here, belongs here. So when you take one of these tensor, you multiply by A is an element of F, and this equals one of these two, okay? So far, so good. This is stuff you knew already. In the next part, I'll speak about things that might be new to you, but I won't go in all details. I will just give a description. Okay, now the problem is, suppose we want to do the same thing with modules. And the reason we want to do it with modules because we want to do it with modules over the group algebra, okay? So let now Mn be two modules over the, let's say, possibly non-commutative ring R. My rings are always unity, although I'm not sure whether this is necessary, ring R, okay? And then we have a problem, because suppose we can construct, oh, this is important, with two right modules, okay? Recall that the difference between a right and left module, but we'll see the detail, is that right module means you have an element of the modules, you have two elements of the ring, and right means that when you apply A, B to M, is A which acts first and then B second, okay? If the opposite happens, then you have a left module, okay? We'll see more details in a second. So suppose you have two right modules, and suppose you are able, suppose you try and construct similarly a tensor product M tensor Rn, okay, which is generated in some sense by elements M tensor N, where of course the two elements are in the right places, and which satisfy the identity we just saw here, okay, that you can switch an A from one side to the other, okay? So that NA tensor N equals N tensor NA, where we have for N in N, and in N, and A in our ring. Well, then we have a problem. And what's this problem? Well, you'll see in a second. The problem is the following. Let A be in R, M and N being, as the name suggests, in the two modules. And then consider what happens when you have MAB, okay, tensor N. And because of this, AB is an element of R, so this should be M tensor N times AB, okay? But in the axioms for modules, we just recall here that this is similar to what happens in vector spaces, except that the objects could be non-commutative, so we have to keep the right order. When you apply the scalars, say AB to M, this means applying first A and then B. Okay, so this means this MA B. But this rule tells me that you have an element of M, in this case the element is MA, which is multiplied by a scalar, an element of R, okay, B. And so this tells me you can bring it to the other side. Let's do it. Okay, so no. Okay, and then you can do it again. You see, you have NA, but on the right you have NB, but that's just another element of N. So you can bring the N to the A to the right. Okay, because that's what you do. You simply take the A to the right. But by this rule, we find that this is. And now you see you have a problem because I have applied 3 times this rule, once here, once here, and once here. And the result are not compatible, okay? Because the ring is in general non-commutative. So AB may be different from BA. And so this does not work, okay? So there's the problem. This problem did not occur with vector spaces because vector spaces are modules, say, over a field, and a field is commutative by definition. And so AB on BA, we switch the 2 factors without even thinking about it. But if you have a non-commutative ring R, and for instance, you could have the group algebra of a non-commutative ring, this could be different. So this does not work. And what is that you should do instead? Well, the trick is the following. The right way of doing it is the following. Take just a second, a right R module M, which I'll write M with R on the right, okay, to say M is an R mod, a right R module, and a left R module N, okay, and do the tensor product as before. I'm not going into the details of how you construct this. It's similar to vector spaces. The problem is that we want to make sense of this, which you cannot do it if you take 2 right modules, okay? And do the tensor product of the 2 modules. Okay, so there are 3 R's, an R here to say that M is the right module, an R here to say that N is the left module. I left the space just to not have clashes, and the tensor product is over R, meaning that for the usual elements, you have that NA tensor N will be M tensor, and look, the point is that this is the right module, the first one, but the second is the left module. So I write AN, okay? And now that there are no problems because you have NAB, okay, times N, which because of this property will be, we can take the AB to the other side, but will be on the left here. Okay, let's check whether this works, because this is NAB. This is the property of the modules, which is inherited by the vector spaces. Say, now you take the B to the other side, okay? But the B will be on the left, because this is the left module. Now you take the A to the other side, but it will be on the left. And then this will be N tensor AB N, which is exactly what we have here, except that I have extra parentheses here. I can safely erase. Okay, so now it works. Okay, and the point is that you move when you move things from left to right, you have to make sure that that this is a right module and this is the left module. Okay. Then the problem, there is only a final problem, that this object, in general, when R is not commutative, because recall that when you were doing the tensor product of vector spaces, the result was a vector space, and whereas here this is not. I mean, if it's not commutative, we have a problem. Why? So you won't be able. You will not be able in general, then in particular case it might be that it works, in general to turn this product into an R module by copying the method for vector spaces. And there is what's the method for vector spaces? The method for vector spaces is that when you multiply it by A, this is equal to MA tensor N, but of course this is also equal to M tensor AN. And why this is impossible, so I'll strike it in red, because you see, if you look at it this way, it's a right module, but if you look at it this way, it's a left module, okay? So this cannot be a module because it doesn't know whether it is a right module or a left module, okay? So I've written the A on the right here, meaning that this will be a right module, but it's a left module if you look at it this way. If I try to define it as a left module, this tells me that it's a right module. So it's not a module, okay? And so in general, this product will only be no, not even a vector, an abelian group. And now I introduce a further complication, but we will see, we'll soon come to the examples I'm interested in. But, okay, let's introduce a concept that you may or not seen. So let N be an abelian group. And RS to be two rings or algebras. Then if N is a left R module and a right S module, well, there are too many thens, but then NRS is called an RS by module. By module, I think that's the correct pronunciation. Okay, so this might look perverse, but you'll see this in a second, a natural example. So an abelian group can be a module over two different rings. And if it's a left module for the first and the right module for the second, that is called an RSB module. Example, we are urgently in need of an example, because this is what we will use for our construction. G is, as usual, a finite group. H is a subgroup of G, okay? And you take for N the group algebra over G, okay? For R, the group algebra over H, and for S, the group algebra over G, okay? And then this is what I'll need in the construction of this induced character. That's why I make these choices, but there are more choices you could do. So the idea is, this is considered a module, okay? You consider N, which is the group algebra, as a left module for R equals CH. How? By left multiplication. And as a right module for S, which is C of G. So these are seen as rings. The CG appears 2 times, but this is in this case it's an abelian group, but this is a ring by right multiplication. Perhaps I'll be back to this on the second, but perhaps I should say that if let's use a neutral notation. If T is a ring, it is naturally a TT bimodule, which we'll write. Okay, it's a T with 2 T's here, where with multiplication on the left and on the right. I've forgotten an important point. I'll be back. So essentially, you have a ring. Okay, if you multiply on the left by the element of itself, this will be a left module, because I mean, if you do something like this, of course, you will have that B acts first. Whereas if you multiply on the right, it's A that acts first. Okay, A, B, T are all elements of T, except that when I write T, I mean an element of the module, say, and these are the 2 rings. Okay, so if you have any ring, you can multiply on the left by the element of the ring itself and get a left module, simply because in the product is B that acts first. Okay, or you can multiply on the right and you get a right module, because between A and B is A that has a chance to act first. And an important thing I had to say here is called an RSB module. It's called if. This is important. If the following identity holds, A and B equal A and B for N in N, A in R, and B in S. This I have to add. Okay, so it's important that the 2 actions commute. Okay, that if you have N, you can first multiply by A on the left and then by B on the right, or first by B on the right and then A on the left, and you get the same thing. And of course, in this particular case, this identity, which I'll call star star, because I think I have already a star from a previous formula, and this formula in this case, star star, in this case, is simply the associative property. Okay, it's simply associative property because you have ATB equal ATB, and this is the associative property because all elements are in T. Okay, except that from a conceptual point of view, when I write it as T is in the module, when I write it AB are in the 2 rings, which are the same. Okay, and so this is a particular case in which I have not taken the full CG, which I could have done, but I have taken CH on the left. So what we obtain this bimodule, which is, and this will play an important role, which is the group algebra acted upon by 2 different rings. On the right, we have the CG, so that's the regular representation. On the left, you have CH. And since I multiply on the left and on the right, it's a bimodule because I'm doing multiplication within CG, but of course, the associative property tells you that you can multiply first on the left and then on the right, or vice versa. Okay. Why is this important? Because we can see, and I'm not going into details, we can see that if MR is a right R module, okay, NRS is a RS bimodule, So N is a left R module and S right module, where R and S are rings. Okay, then the tensor product over R of this, which remember is not anymore a right module, an R module anymore, because you don't know whether it's left or right. This is a right S module with M tensor N A equal M N A. Okay, A in S and Mn in M and N. This time there is no conflict, because S lives on the right here. You are switching. Remember that we have N. Let's use a different letter. We have MR tensor N equals M tensor Rn for R in R, but S is a different thing. I mean, this is an action on the left here, and this is action on the right. So this R does not come out, but the S here you can safely put here, because there's nothing to tell you that this product on the right can be moved to the other side. So there's no contradiction here. Okay, why is this construction important? Because I will set things up and then continue next time. Because the problem I want to address is the following. So let G be a finite group and H be a subgroup of G. Okay, so if rho is a representation of G, okay, then you can consider the restriction to H, and this is a representation of H. Okay, this is trivial, because this is a morphism, so it means that for all the G1, G2, you have rho G1, G2 equals rho G1, G2, and if you restrict to H, of course, a fortiori, as we say, it satisfies the same property. Okay. Good. So, and this is the restriction. But conversely, given a representation sigma of H, H is always subgroup G. Is it always the case that sigma is a restriction? So this is the, okay, restriction, okay, is a restriction of the restriction of sigma equals rho restricted to H for some representation R. Rho of G. And the answer, unfortunately, is no. Not in general. And why is this not true in general? Of course, if I'm saying that this is not true in general, it suffices to give you an example. And the example we have is the following. Consider G equals S3 and H to be the subgroup generated by 1, 2, 3. So we take G to be S3, H to be 1, 2, 3, and we take as what letter was I was using? Sigma. Yes, sigma a linear character. Actually, the linear character of H, such as sigma of 1, 2, 3 is omega, a primitive third root of unity. So essentially, sigma, so sigma of of 1 is 1, sigma 1, 2, 3, where I avoid the double parenthesis omega, and sigma 1, 2, 3 squared, which is 1, 3, 2, is omega squared, okay? But this clearly cannot be the restriction of it's a linear character, okay? So it's a representation of degree 1, of dimension 1. It cannot be the restriction of a linear. Of course, if it's a restriction, okay, if sigma equals rho restriction to H of a representation rho, then of course, yeah, the sigma 1, since 1 is in H, is rho H1, is rho 1, then means rho is also a linear character. But then there is a problem because you see that on H, this is not class function, but this is not a class function, okay, on G. But the problem that but such a rho could not be a class function. What does it mean? So it's a linear character, okay? Say it's a linear representation of degree 1, so 1 times 1 matrices. But remember that representation of G are class functions of G, and because 1, 2, 3 and 1, 2, 3 squared, which is 1, 3, 2, are conjugate in G in S3. But the values but the values are different. So sorry, let's continue. No, well, no. I'll continue here to have this at our disposal, because I mean, if sigma is the restriction of rho to H, then what we have is that rho 1, 2, 3. So on H, rho has the same value of sigma. So rho of 1, 2, 3 is omega, and rho of 1, 2, 3 squared is omega squared, and the two are different. And this is a contradiction because rho is a class function on G, okay? So rho is not a class function on G. And then also you can see that if you look at the linear characters of G, you see that there is no linear character that takes this value. So in general, whereas you can always do restriction from top to bottom, you're not always allowed to go in the other direction. So the method to remedy this there is something that I will be discussing in the next lectures. There is a method of induced representations and characters. Which, however, cannot work wonders. So, in general, these methods, which we'll use in one version, the tensor product they have discussed, in general, if sigma is the restriction of H, this method will not reconstruct rho from sigma, but will construct, say, a representation of G, which at least contains sigma. So what I mean here, that sigma is a representation of H, and rho is a representation of G. So there is no miracle way of of constructing raw if there is raw, and something else if there is no raw. But the method will construct a representation with, in this case, it will be larger. And I repeat, one of the methods to do this is with tensor product, but in any case, we construct a representation we will contain sigma. And I think this is a good moment to stop. So next time we will be seeing how to do this method of induced representations and characters. We will first see the idea of the representation of the induced representations in two different ways, because this is rather important. And then we see that when it comes to character, there is a relatively simple formula, which will come quite naturally, for instance, from this discussion of tensor product that we've done, that explain how to construct the induced character starting from the character from a subgroup. So that's all for today. Thanks for listening.